Hello everyone. In this video, we're going to talk about how the definite integral can be used to find the average value of a function. To motivate this concept, I've just given us an example function to work with here, which I've called f of x. You'll notice that I also marked the x-axis with two values, which I called a and b. So here's the big question in this video. How can we find the average value of f of x over this interval which starts at x equals a and ends at x equals b? First of all, I want to clarify what I mean when I say average value. So keep in mind that f of x is another name for the y value. So when I say the average value of f of x, that really means the average y value among all the points on this curve. And here's one way you can visualize that concept. If you were to think about how high above the x-axis each of the points on this curve are on average, you'd probably eyeball it somewhere around where I placed this blue line. And since the height of each point is represented by its y value, this blue line can be thought of as a visual representation of what we mean by the average value of f of x. From here on out, I'm going to use this notation f with the subscript av to denote this average value of f. Okay, f av is really the value of y, which corresponds to that blue line. And what we'd like to know is, how do we find that value? And clearly just eyeballing it like I've done here isn't a very convincing method. And so while on one hand you could say that finding an average is simple, since all you have to do is add up all the things and then divide by the number of things, but upon trying that, you would immediately notice a problem. And the problem is that this curve really contains infinitely many points, which would need to be included in our average. And of course, we can't add together infinitely many things. But as it turns out, there's a simple formula involving the integral, which we can use to find the value of f av. At this stage, I'm going to suggest that you start creating a formula sheet for this course. And anytime I present you with a new formula, you can add it so that you have all the formulas together in one place. Okay, now I haven't explained where this formula comes from yet, and you can rest assured that I will do that in the next video. But for the time being, just trust me that this formula is accurate, and we'll work through a couple of examples first. So here's our first example. Find the average value of the given function on the closed interval between x equals 0 and x equals 1. So let's work through the solution to this problem together. Since the question is asking us for the average value of a function, we can start by writing down the formula for f av, which was just given on the previous slide. So first we have 1 over b minus a, which in this case, we can see that a equals 0 and b equals 1. Those are the endpoints of the interval. And this gets multiplied by an integral from a to b. And the function we integrate is the one that was given in the question, the one that we want to find the average of. Okay, just don't forget to include this dx, which is an important part of using the notation properly for integrals, and I will be picky about that when I'm grading your work, just so you know. Now, let's just clean this up a bit. We know that 1 over 1 minus 0 is just 1, so there's no need to multiply by 1. And now all we need to do is calculate the value of this integral. Now, you should be capable of doing that based on what you learned in your first calculus course. But let me remind you of some of the important techniques that you're going to need to remember from this point forward. We know that calculating an integral amounts to finding an antiderivative. At this point in time, I'm assuming that polynomials and basic trig functions are really the only things that you know how to antidifferentiate. But if you have a function which is any more complicated than that, such as the one that you see here, you might find the method of u-substitution is helpful. So let's remind ourselves of how to do that. First, we need to make a choice of what we want to make u equal to. There are some things to consider about what makes a good choice, but for now I'll just tell you that 1 minus x is the correct choice. So we're going to let u equal 1 minus x, and that allows us to express the integral as the integral of x root u. Whenever we perform a u-substitution like this, it is important to remember to express the entire integral in terms of u, and that includes this dx, which we'd like to turn into a du instead, if possible. We know that the relationship between du and dx can be found by calculating du over dx, or in other words, the derivative of u with respect to x. Since we know that u equals 1 minus x, we know the derivative of that is just -1. So now we can use this relationship to express dx in terms of du, which is what we want to do. To do that, we multiply both sides by dx, which shows that du equals -dx. And then multiplying both sides by -1, we can see that dx equals -du. And that means that where we see dx, we can simply put -du instead, since after all, that's what dx is equal to. And don't forget, we're still evaluating this integral from 0 to 1. But something you should keep in mind at this stage is that 0 and 1 are x values, not u values. So to avoid confusion, I'm going to state the lower limit as x equals 0, as I've just shown there. And likewise, I'm going to state the upper limit as x equals 1. And just for cleanup, we know that this negative can be pulled out front of the integral. Okay, the fact that you can do that is something that you should remember from your first calculus course. Keep in mind that you're allowed to do that with any constant that has been multiplied to your function. And furthermore, that's the only situation where you can pull something out like this. So it has to be a constant. Now at this stage, I hope you recognize that the biggest obstacle standing in our way is the fact that we still have this x left over in our integral. So before we proceed any further, we need to make sure everything has been expressed in terms of u, and that includes this x. We need to express this x in terms of u. Whenever this happens, when we have leftover x's, the key is to remind ourselves of what is the relationship between u and x in the first place. Okay, earlier on, we decided that u is equal to 1 minus x, and we can simply rearrange that relationship to figure out what x is equal to in terms of u. A bit of basic algebra there shows us that x is equal to 1 minus u. And that means that where we see an x, we can put 1 minus u instead. Of course, we still have root u du to account for from the previous step. I've just given myself more space and summarized what we've done so far to find f av. Okay, we've managed now to express the entire integral in terms of u, which is good, except that, as I noted before, these integration limits are still values of x, and it would be preferable if they were values of u, just like everything else we've done so far. So we would like to express our integral like this. What values of u would correspond to the x values of 0 and 1? Well, to figure that out, we can make use of the fact that we know u is equal to 1 minus x. So for the bottom limit, we had x equals 0, and that would imply u is 1 minus 0. And at the top, we had x equals 1, which would imply that u is 1 minus 1. Right? Both of those were just computed using the formula u equals 1 minus x. If we simplify those values, we end up with u equals 1 on the bottom and u equals 0 on the top. And now that everything's been expressed in terms of u, we're almost ready to find our antiderivative. But to prepare for that, I'm going to express root u as u to the 1/2. This next step I'm about to show you is actually optional, but you might remember from your previous calculus course that a simplification can be made whenever a negative is applied to an integral like this. So more specifically, applying a negative to an integral has the effect of interchanging the integration limits. So while before we had an integral from u equals 1 to u equals 0, if we apply the negative, we can change this to an integral from u equals 0 to u equals 1. And if we switch the integration limits like that, we no longer need to carry around the negative in front, which is just kind of a nice thing. But again, it is optional. So we've reached this point where everything has been cleaned up nicely and expressed in terms of u. But what you'll notice is that the function we're integrating contains two factors which are being multiplied together. And as I hope you remember, multiplication creates problems for us when we're trying to find derivatives and antiderivatives. Right, for derivatives, you would need to use the product rule, but there's no such thing as a product rule for antiderivatives. But at least in this situation, we can avoid that problem by expanding everything out. So the first term would get multiplied by u to the half, and that would result in just u to the half. The second term also will be multiplied by u to the half, resulting in u to the 3/2. And I hope you're not forgetting that all of this still gets multiplied by du, keeping with good notation the whole way along here. Now that we've expanded everything out, we have finally reached a form where we're ready to antidifferentiate. So if you remember how to antidifferentiate, for u to the half, the power rule says to increase the exponent by 1, so we would get u to the 3/2, and then you would divide by that exponent. The same method can be used for the second term, where u to the 3/2 will become u to the 5/2. We don't need the integral symbol anymore since we've now taken our antiderivative, but don't forget that this entire expression still needs to be evaluated at u equals 0 and u equals 1. Remember that dividing by a fraction is the same as multiplying by its reciprocal, and so I suggest doing that just to keep things looking tidy and organized. So, for the first term, instead of dividing by 3/2, we can instead multiply by 2/3, and that just helps us not have to deal with fractions inside of fractions. Likewise, instead of dividing by 5/2, we can multiply by 2/5. All that's left to do now is evaluate this expression at u equals 0 and u equals 1. You should remember that the way you do that is first plug in the upper limit, which is u equals 1, then plug in the lower limit, which is u equals 0, and subtract the results. So this is what we get when we plug in u equals 1, and this is what we get when we plug in u equals 0. At this stage, it's just routine simplification, so you can check these remaining details for yourself and verify that the final answer is 4/15. This number represents the average value of our function on the given interval. I hope that last example was a pretty good refresher of a lot of different concepts from your first calculus course. We'll be using the method of u-substitution quite a lot in this course, so I want to spend a minute offering some tips about how you can make a good choice of what u should be equal to when you use that method. So remember that u-substitution is really a way of undoing the chain rule, and that rule has to do with functions which are nested inside of other functions. So whenever you see functions inside of other functions, that might give you a hint that u-substitution could be a good idea. And in those situations, it can be useful to let u be equal to the inside part. So for example, if you reflect back on the problem we just worked on, the correct choice was to let u equal 1 minus x. And the reason that turned out to be a good choice is because 1 minus x was the inside part of the square root. I should be clear that letting u equal the inside part isn't something that will necessarily always work, but it's something that's at least worth thinking about whenever you see functions inside of functions like this. Another thing that you should look out for is letting u equal something whose derivative appears as a factor. Let me show you what I mean by that. Consider this integral of tan x times secant squared x. It turns out that the correct choice here is to let u equal tan of x. And here's the reason for that. You should remember from your first calculus course that the derivative of tan of x is secant squared of x. And as you'll notice, secant squared x does appear as a factor in our integral. So according to the tip I've given here, this might make a good choice of u. But to convince ourselves of that, we can quickly work out the details to understand why it's important to have the derivative appearing as a factor like this. So if we do let u equal tan of x, we know that we still need to calculate du. But that's easy. Just take the derivative to find out that du is secant squared x dx. And the really nice thing about that is that secant squared x dx is something we can literally see right here in our integral. We've just seen that that entire thing is literally equal to du. And tan x is just another name for what we called u. So putting this together, we can see that we end up with a pretty simple integral. So the tip I just gave us did actually leave us in a useful direction. If you take a moment to reflect on why it's important to see the derivative of u appear as a factor, it's really because the derivative of u is always going to appear in the formula for du. So this just helps us ensure that du behaves as nicely as possible as we just saw in this example. Keep in mind that there's no recipe I can give you for solving every single type of integral problem, but these are at least some common tricks to add to your box of tools. Right? Anytime you see one of, or especially both of these patterns that I just mentioned, it's a good hint that u-substitution is very likely the correct method for solving your integral. So with all these tips in mind, let's quickly work through another example. Find the average value of this function on the given interval. So just like before, you can start with the formula for f_av, which I gave you at the beginning of the video. And to keep things easy, let's simplify this coefficient. In the denominator, I see pi minus pi over 2, and that would simplify to pi over 2 on the bottom. Like we saw before, division by a fraction can always be viewed as multiplication by its reciprocal, and so this coefficient simplifies to 2 over pi, and so this is what we end up with. Now, the function we need to integrate is not a polynomial, and it's not a basic trig function. There's a bit more going on here. So that means that the substitution method is something that we should be thinking about. The question then becomes, what should we let u be equal to? I want you to pause here and look back to the tips I gave you just a moment ago and see if you can use those tips to come up with your own guess about what we should let u be equal to. I'm about to spoil it, so make sure you're ready before you continue. It turns out the best choice here is to let u equal sine of 3x. And that's because sine of 3x actually matches both of the tips that I gave you. For starters, it's a function which is inside another function, since sine of 3x is being squared. And secondly, when you go to compute du, you'll notice that the derivative of sine of 3x does appear as a factor in our integral. Well, not exactly, since the chain rule tells us that the derivative of sine of 3x is actually 3 cos of 3x, but at least cos of 3x appears as a factor in our integral, so that's pretty close. Now, the advantage of this is that it's easy to take this entire expression, cos of 3x dx, and put it in terms of u with just a bit of basic algebra. By dividing both sides by 3, we can see that it's really equal to 1/3 du. In other words, this whole thing can be replaced by 1/3 du, since that's what this expression is equal to after all. Now let's put all this together. We know that sine squared of 3x is really just another name for u squared. And cos of 3x dx is another name for 1/3 du. So I'd say the substitution is working out pretty nicely since we've gotten rid of all the x's, except we need to remember that our integration limits themselves are still values of x, so we should change them into values of u just like we did in the previous example. To do that, we just need to remind ourselves of what u is equal to. When x is pi over 2, sine of 3x would be sine of 3 pi over 2. And when x is pi, sine of 3x would be sine of 3 pi. So I've changed those into u limits in exactly the same way that I did in the previous example. And also, just like in the previous example, any constants which are being multiplied in here can be pulled out front. That gives us 2 over 3 pi in the front, times the integral of u squared du. And if you remember your trig, which of course I expect that you do, you'll know that sine of 3 pi over 2 is -1, and sine of 3 pi is 0. So those upper and lower limits can be calculated and simplified in that way. So we've boiled the problem down to this relatively simple integral, and I trust that you should be capable of working out the rest on your own from here. So you can pause and check these remaining details for yourself if you'd like, but I'll wrap up the video here. We saw some examples of how to find the average value of a function, but I haven't yet shown you where the formula we've been using actually comes from or why it works. So stay tuned for that in the next video, and I will see you next time.